This is part 9 of the series Integration, and we're continuing on with some practice evaluating integrals using FTC1, the first fundamental theorem of calculus, or the fundamental theorem of calculus, part 1. So in this problem, we have the integral from 0 to pi over 4 of secant squared x dx. Now the way I work these trigonometric integrals is I try to figure out what function has a derivative equal to the integrand. So what function has a derivative equal to secant squared? Well, the derivative of tangent is secant squared. So the antiderivative of secant squared must be tangent. So to evaluate this then, we have this is tangent x evaluated from 0 to pi over 4. And this is tangent of pi over 4 minus tangent of 0. So tangent of pi over 4 is 1, and the tangent of 0, well, tangent is sine over cosine, and the sine of 0 is 0, so this is 1 minus 0, so this integral is just 1. So these trigonometric integrals aren't so bad on the surface as long as you can remember the basic underlying techniques. So let's move on to the next problem. In this problem, we need to find the integral from 0 to 2 of the absolute value of 2x minus 1 with respect to x. Now, since we haven't seen any rules that handle absolute value functions per se, we're going to have to get a little bit creative and see if we can use some of the properties of antidifferentiation and integration to work this thing out. Now, the concept of absolute value, you can see that the vertex is sitting here, and to the left of the vertex, the function 2x minus 1 would ordinarily be negative. But because we have absolute value and there can be no negatives, it goes positive here. So we're going to use that idea. So the first thing is we're going to find where this vertex is. And the vertex is where this piece is equal to 0. So where 2x minus 1 equals 0 is going to be our vertex. So 2x equals 1 and x equals 1/2. So we know that at this point, at x equals 1/2, that's the vertex of our absolute value function. So what we're going to do is we're going to assume that our function of integration is simply 2x minus 1, and we're going to create two regions, a region from 0 to 1/2, and then a region from 1/2 to 2, and we're going to combine those two to give us the total area under this curve. And because the function 2x minus 1 is negative to the left of that vertex, so this is all negative area, we're going to actually change the sign of that integral. So let's go ahead and put this down and see if we can figure out what's going on here. So this is the integral from 0 to 1/2 of 2x minus 1 dx. And we want the negative of that because this value is actually going to be negative. And we want to add it, so we want to make it positive. Then we're going to add to that the integral from 1/2 to 2 of 2x minus 1 dx. So to go ahead and evaluate that, we'd have negative, and the integral of this is 2x squared over 2 minus x, evaluated from 0 to 1/2, plus this same antiderivative. These 2's cancel out, so we can go ahead and simplify that right off the bat. X squared minus x, evaluated from 1/2 to 2. So again, we said that these cancel out. So let's evaluate this. We have negative 1/2 squared minus 1/2 minus 0 squared minus 0 is just 0. so that term disappears, plus 2 squared minus 2 minus 1/2 squared minus 1/2. And let's continue this evaluation. So 1/2 squared is 1/4, minus 1/2 is negative 1/4. Negative 1/4 times negative 1 is 1/4. Plus, that's 4 minus 2 is 2, minus, this is 1/4 minus 1/2, so that's negative 1/4, and negative times negative is positive, so that's plus 1/4. So that gives us 2 plus 1/4 plus 1/4 is 2 plus 1/2, which is 5/2. Alright, now let's move on to another example. In this example, we're supposed to find the region bounded by the graph of this function, the x-axis, and the vertical lines x equals 0 and x equals 2. So they didn't give us the actual integral. We're going to have to come up with that on our own. So that's not too bad. Let's go ahead and put in our integral symbol. And our lower limit is 0. Our upper limit is 2. And our function is 2x squared minus 3x plus 2. And we're integrating this with respect to x. So we can go ahead and take the antiderivative of this, and that gives us 2x to the third over 3 minus 3x squared over 2 plus 2x evaluated from 0 to 2. And now we do our evaluation. There's 2 times 2 to the third over 3 minus 3 times 2 squared over 2 plus 2 times 2 minus 0 minus 0 plus 0, so that's just a 0. So 2 to the third is 8. 8 times 2 is 16, so that's 16 thirds, minus 4 divided by 2 is 2. 3 times 2 is 6, plus 4. So this is 16 thirds minus 2, and 2 is the equivalent of 6 thirds, so 16 minus 6 is just 10 thirds. After a little bit of practice with the homework assignment, you shouldn't have any problem with these. So let's go ahead and move on to the next section. Here we have a new theorem called the mean value theorem for integrals. And what it says is if function f is continuous on a closed interval ab, then there exists a number c in the closed interval ab such that the integral from a to b of that function with respect to x is equal to f of c times b minus a. Now, if we put this in simpler terms, it's simply saying that the area under the curve, the area under this curve, is going to be equal to the area of a rectangle whose width is b minus a and whose height is the function f evaluated at some point c. So this is the height and width of the rectangle. Now, this is an existence theorem, just like some of the theorems that we had from our differentiation lessons, and it tells us that a c exists, but it doesn't exactly tell us how to find that c. But if we go one step further here, we look at this piece, and the average value of a function is evaluated if we divide the mean value theorem by the term b minus a. This f of c equals 1 over b minus a times f of x, the integral of f of x dx. So that tells us that the function f evaluated at c equals this average value of the function. In other words, this height here, this level, is the average value of the function. And so to find our c value for the mean value theorem, that's all we need to do is find what x value of the function gives us this y value up here. So it wouldn't be really tough to do. But this is an important expression. This is the average value of a function, and it's directly related to the mean value theorem. So let's go ahead and put this into practice and see how this works out. So in this problem, we're asked in a pretty straightforward manner to find the average value of the function 3x squared minus 2x on the interval from 1 to 4. So the average value is given by 1 over b minus a times the integral from a to b of f of x dx. So that's 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx. So we'll go ahead and take this antiderivative. That's 1/3 times, this is x to the third over 3. Those 3's cancel out, so that's simply x to the third, minus, this is x squared over 2, so the 2's are going to cancel out. So x squared evaluated from 1 to 4. So again, that's 1/3 times, that's 4 to the third minus 4 squared minus 1 to the third minus 1 squared. So that's 1/3 times 4 to the third is 64 minus 16 minus 1 plus 1. So those go away, and it's going to be in the final, it's going to be 48/3, which is 16. So 16 is the average value of our function on this interval 1 to 4. All right, let's move on to the next section and see what we have.